Alright, so in this video we're finally going to look at solving systems of three linear equations, which I've done in a couple other videos using elimination and back substitution. But now we're finally going to look at how to do it with what are called matrices using a technique called Gaussian elimination. Okay, so uh, we'll talk about what matrices are and then how to use them to solve systems. So let's get an example here. So if I want to solve this system of three linear equations using matrices, so let's actually specify that in the instructions. Solve using matrices and Gaussian elimination. Okay? And so, in fact, this video focuses only on Gaussian elimination. There's another technique called Gauss-Jordan elimination, which requires more matrix work, but you don't have to know that to solve systems. So let me mention that the word matrices is plural for matrix. And a matrix is just a table of values, basically. So the first thing we would do is convert this system to an augmented matrix. So an augmented matrix. What matters before you create your augmented matrix, the goal is to only use the coefficients here and avoid the x, the y, the z, the equals. Leave all of that out. If you want to leave all of that out, you have to assume this is written a certain way, and it is. We need all of our x's in the first column, all of our y's in the second column, which, by the way, this is the same thing as plus 0y, all of our z's in the third column, equals, need your equals next, and you need your constants in the fourth column, okay? And so if it's set up like that, then you can directly translate that to an augmented matrix, which is just a table of values again. So the table of values are going to be the coefficients. So our first row is going to be a 2, a -1, a 4, and a -3. Now leave space between those because you don't want to think of this right here maybe as -14, right? So you need to leave enough space. Create distinct rows and columns. Our next row is going to be a 1, a -2, a -10, and a -6. And our last row is going to be 3, 0, 4, 7. And to make it a matrix, this is a table of values, but to make it a matrix, to indicate that it is a matrix, we put brackets around it. And to make it an augmented matrix, we separate where the equals is. So the equals corresponds to this vertical line in the matrix. And now we know what this represents. 2x minus 1y plus 4z equals -3. 1x minus 2y minus 10z equals -6, etc. So now to solve the system, all we have to do is do what are called row operations on this matrix. And row operations, just like when you solved systems, row operations, you can multiply a row by a constant, not 0 of course, and add to a row. You can simply multiply a row by a constant, just like with systems, and you can even interchange two rows, put them in a different order, because it's still the same system, right? If the equations are written in a different order, it's still the same system, so you can do that. Now, so in order for that to happen, to solve this, what you want, just like if you were to solve the system, you would try to get rid of x's, and then you try to get rid of y's, so that you're only left with a z in the third equation. The second equation would just have y and z, and the first equation would have x, y, and z. So in other words, you want to create your stair-step kind of scenario like this, like we did with a system. And what that means in a matrix is we want all of these to be zeros, okay? So that's our goal, turn those into zeros. So let's get started just like we do with a system. I need to take this guy and turn these into zeros. Now that's kind of hard because 2 is not very easy to cancel with these if I multiply and add. So what I'm going to do is 1s are very easy to use. So I'd like to make this 1 go up to the top row. So what I'm going to do is interchange row 1 and row 2. Okay, so I'm going to get a new augmented matrix. My first row is now going to be what was my second row. So 1, -2, -10, -6. And my second row is going to be my previous first row. And again, I'm doing that because 1s are easy to use to cancel things out. So here's my new augmented matrix. It's equivalent to what I had before. Now, what I can do is I can take this 1 and turn it into a -2 to cancel that 2. So I'll take -2 times row 1 and I'll add it to row 2 to get a new row 2. And to cancel my 3, I'll multiply my row 1 by -3. So -3 times row 1 plus row 3 is going to give me my new row 3. So let's see what that looks like. -2 times row 1 is going to be -2, +4, +20, +12. Plus row 2 is 2, -1, 4, -3. And my new row 2 is going to be 0, 3, 24, 9. That's going to be my new row 2. Now let's work on row 3. So -3 times row 1 is going to be -3, +6, +30, +18. Plus row 3 is going to be 3, 0, 4, 7. So I get 0, 6, 34, 25, and that's going to be my new row 3. So let's write my new augmented matrix. Row 1 didn't change, so 1, -2, -10, -6. Then my new row 2 is 0, 3, 24, 9. And my new row 3 is 0, 6, 34, 25. Okay, very good. Now I'm looking at this. I don't really like the numbers a lot. They're kind of tough to work with. But I noticed that row 2, 3, 24, 9, even 0, I can easily divide those by 3 or multiply them by 1/3. So I'm going to take 1/3 times row 2 and replace it with row 2. Okay, so my first row doesn't change. My second row is 0, 1, 8, 3. It's the same thing as dividing everything by 3. My third row, I can't do that because nothing goes into 6, 34, and 25, so I'm stuck with that guy. But I do get a simpler augmented matrix to work with. Now what I need is this guy, this 6, to be a 0, and I'll do that by turning this 1, luckily it's a 1, into a -6. So I'll take -6 times row 2 and add it to row 3 to get my new row 3. So that looks like -6 times row 2 is 0, -6, -48, -18, and I need to add that to row 3, which is 0, 6, 34, 25. Adding, I get 0, 0, which is good. Let's see, -14 and +7. And that's going to be my new row 3. So let's copy row 1. Let's copy row 2. And let's copy our new row 3. Now we've got what's called, well, we're close, right? We've got our stair-step effect. You could stop there and start to work because you know that this third equation is 0x plus 0y, so there's no x or y. Negative 14z equals 7, so you could use that to go ahead and solve for z. However, what we could do is, if I wanted to make this a 1, to get what's called row echelon form, so let me write that out here. I'm only mentioning it because lots of books use it, so I better mention it, is when you get basically you get a first entry in each row of a 1. So your next entry, your next row can't have a 1 under this one, but it could have zeros, and then it'd have a 1 eventually as its first non-zero entry. And then the next row would have zeros, followed by finally the first non-zero entry would be a 1. And that just makes it easy to solve systems if they're all 1s. But it's certainly not necessary. Okay, so I'm going to go ahead and do it here just because it's common practice. But like I said, you could go ahead and say negative 14z equals 7 and solve for z. And then you could back up and do substitution into the second equation to get y, and back up to the first equation to get x. Okay. Okay, so what I'm going to do is turn this into a 1, this negative 14 into a 1, by taking negative 1/14, or I'll divide by negative 14 basically, times row 3, and that's going to give me my new row 3. So I've got 1, negative 2, negative 10, negative 6, 0, 1, 8, 3, 0, 0, divide by negative 14 and I get 1, divide by negative 14 and I get negative 1/2. Okay? So now I know that 0x plus 0y plus 1z, so just z, equals, because of the vertical line, negative 1/2. So that tells me my z directly. And then I can back that up. My second equation is 0x plus 1y, so y, plus 8z equals 3, and I can plug negative 1/2 in for z. So I get y, 8 times negative 1/2 is negative 4, equals 3, so y is 7. All right, and then I can write down my first equation. So my second equation came from this guy, and my first equation is going to say x minus 2y minus 10z equals negative 6. And I can plug both of my previous values in for z and for y, and I can solve for x. So x minus 2 times 7, so x minus 14. Negative 10 times negative 1/2 is positive 5, equals negative 6. Okay, so negative 14 plus 5 is negative 9. Add 9 over, and I get 3 for x. So my solution to the system that I started with is the ordered triple where x is 3, y is 7, z is negative 1/2. So by working with matrices, augmented matrices, you eliminate having to write all the variables over and over again, and you just get to work with the coefficients. And the operations, the row operations, are exactly the same as they are with a system. Okay, and you can get things like 0, 0, just like we have with other examples, and you can get inconsistent systems, you can get an infinite number of solutions, you can get no solution, but here's a general example where you get one solution. And I hope it makes sense. It takes quite a bit of practice. You've got to be really detail oriented, very organized, so I encourage you to take your time and make sure you're getting it all right as you go along. Good luck.